So good afternoon, everyone. My name is Julien Perez. I'm actually the lead of the machine learning and optimization team at the Naval Labs Europe. As you know, it now is in France, in Grenoble to be precise. And the talk of today is actually to share with you some of our current research and results in the domain of deep learning and what we call differentiable reasoning machine. I will start my talk by explaining that term that maybe you don't really know, which is actually differentiable reasoning machines. And my goal here is to explain how actually deep learning, which is actually a family of models, become today a true programming paradigm. And from this, I will introduce the two main objects that will be the research in this talk, which are the usage of memory and attention for reasoning tasks. Then, in terms of reasoning tasks, we will study together three language-related tasks that we are strongly interested in. First one is machine reading. The second one is dialogue state tracking. And the last one is end-to-end dialogues. And we will see how on those three tasks that we will define, a reasoning capability is actually necessary and useful to start obtaining interesting results. And I will finish this talk by giving up new, I would say, further work that might be actually inspire you for your own research, I would say. So first of all, differentiable reasoning machine. In order to explain that term, I need to come back to the very definition of actually a computer program and computer programming. As we know, a computer program is basically a sequence of information, a sequence of decision, a sequence of order that are actually handcrafted in order to perform a specific task. From that field emerged around 30 years ago the field of machine learning, which had actually at the very beginning two main objectives. The very first objective of machine learning was actually to be able to produce software where actually it was impossible or maybe very difficult to produce it by hand. Obviously, one of the very known type of application are actually image classification or even text classification. Another motivation for machine learning was the capability to have systems that will be actually able to customize themselves once deployed, when it's not possible to do it by hand once they are deployed. So we end up with this very classic architecture when actually a process is actually driven by input and a backend and produce output. But through time actually, we have actually changed this handcrafted process by a differentiable function. A differentiable function is defined by an input space, project over an output space, is defined by a topology of parameters and the fact that it is optimizable and, if possible, differentiable. So when you define this thing, actually, you have defined the kind of model that are actually mostly used today by the domain of computer vision, natural language processing, automatic speech recognition, and all the domain of what we used to call deep learning. So when deep learning was defined, it was defined by the capability to project any output space from an input space. But it was actually more than that. Because what we want to be able to do is to create identifiable capabilities. We want to have programs that have capabilities that then we train through a certain error to minimize. And the problem we have is that very recently, as you know, for example, for the domain of machine translation, we observed that something was missing. That the type of model we used to know, like convolutional neural network or fully connected layers of perceptron, was not enough to perform translation or summarization or that kind of task. We knew that the problem we had was the capability to have models that have actually memory in order to deal with those sequential data. And more than that, we want to have models that are able to actually take as input very large input space and then be able to automatically choose into this input space what are the elements that are relevant for the task. And here come and a very last thing that was also quite important was the capability to interpret the decisions of the model. And the building block of attention and memory that I will actually use in this talk are actually choose for these specific capabilities. And so, as I said before, I will show how actually this kind of architecture that you see here is actually necessary, at least very useful, for machine reading, state tracking, and end-to-end dialogues. So first of all, machine reading. The definition of machine reading is fairly simple. Assuming a text, assuming a question, I want to be able to answer those questions by using examples of that kind of triples. So basically, I want to be able to learn how to answer a question by having a huge amount of text associated with question and a given answer. So in a sense, machine reading is a formal supervised machine learning task for text comprehension. We can imagine how important that kind of model can be for information extraction in collection of documents, for mining information in the social media, for security on the web, and for dialogue system. Another very important feature of that kind of model is the necessity to not have to anymore duplicate the data. When people make information extraction from text, what they basically do is that they duplicate the information that is actually already present in the text in order to make it machine understandable. What we do here is we try to make the text machine understandable. A very simple example I can give you for the necessity of that kind of model is if you are basically a social network. A social network is around several billions of lines of text every day. Do you want to have to duplicate this information in order to be able to understand them? No, you don't want. So what you want is the text to become the knowledge base. That's what we try to do. And actually, we are not the only one. Since 2 years now, a huge amount of universities, Stanford, Oxford, University of Paris-Jussieu, has actually started to develop that kind of data sets for machine reading. On the left-hand side, you see a very first type of machine reading data set that we call ranked type of machine reading. Here the game is, I give you a small piece of text, I give you a question, and I will give you a set of possible answers and you will have to rank them. On the right-hand side, what we call in this case close form type of question, I will give you a piece of text, I will give you a question, but you see, the question is actually a sentence, it's a statement, when one element was actually replaced by a placeholder, an X. And what you will have to do in this case is to find in the text what is the piece of text you should replace by the X to actually produce an answer. You have also other type you have also another tab that has been also proposed that is derived from this one, where I actually give you a true question, not this type of question, and you will have to find in the text the span, the piece of text that corresponds to the answer. In this case, we call that extractive machine reading. One of the very first models that was proposed was actually taken from CNN news. And the idea was to take a news, to take the synopsis of the news and to throw away, to blank a piece of text into the synopsis, into the summary. And then the summary became the closed form question. It was DeepMind in 2015 with the team of Phil Blunson that proposed that approach. And the first model that they proposed in order to handle that problem was based on LSTM type of architecture. What you see here is the first bi-LSTM that takes as an input the word embedding of the text. What you see on the right-hand side of the model is another bi-LSTM that takes as an input a possible clause. Here, for example, the X will be replaced by a candidate answer. And the R here that you see here will be actually a combination of the transformation of those words embeddings with what you see actually here, which is actually an attention value. So basically, you will actually create this R here as a linear combination of that attention-based representation of each of the piece of text. So here, the representation of each of the vector here is conditioned by the value of this vector here, which is the representation of the question. And actually it makes sense, because if I ask you to answer a question, I mean, if I ask you to read the text and then ask the question, or if I give you the question before, and then I ask you, and then you read the text, you will not proceed the same way. So that's what that kind of model is trying to do. A very close type of model that was proposed by IBM this time in 2016 was actually proceed very closely. Here, you take the sentence and you transform each of the words using a BiLSTM model, and here you use a second BiLSTM model to transform the question. And then at that stage here, you perform a dot product, the dot product that is actually somewhere here. You perform a dot product between the representation of each of the words transformed by the BiLSTM and the representation of the question. And then you just compute for each of the words that are present in the text, what is the score? And this type of model, that is actually an extractive type of question answering, has actually provide pretty good result for the data set I was presenting just before using CNNs. But we had actually a problem. In 2016, Christopher Manning, which is the head of the Stanford Computer Science Lab, showed that with a very good logistic regression and a lot of feature engineering, he was actually able to make better than those two models. So you can tell me, but okay, so what are we doing here? What he was trying to explain, and I come back to what I said before, is not the error that is important, it's the capability you try to model. What he showed here was actually the text was actually not so difficult. And actually having feature engineering and a good logistic regression was enough. But was enough instead for one type of model that you see at the very end, the memory network. So here, I will start by developing on the first statement, the fact that the text was not difficult enough. In 2015, to actually answer that problem, a lot of people started to actually create text where reasoning capability was explicitly present. The most famous one is actually the baby task of Antoine Borde and Jason Weston, where actually 20 type of small text was associated, each of them, by a specific type of capability. As you see here, you have the counting capability, yes, no question, maintaining a set or a list, answering a question with several supporting facts that needs to be used. And so at the end of the day, what that type of text was trying to explain is that we needed to have a data set where the reasoning capability was explicitly present. So here, if we want to solve that problem, you need to have a model that have that capability. And at that time, the model that was proposed is called, maybe you know it already, memory network. A memory network is basically a simplifying neural Turing machine without the writing aspect. The only thing that you will write, as I will show after, is the controller. You only read the memory, but you read it in a sequential time, in a sequential manner, by updating a reading controller. So more concretely, the idea is basically to encode your text. I don't see it very well. On the very right-hand side of the slides, so the text is cut into pieces. You can decide the type of pieces that you need. It might be the sentence, it might be the words, it might be a certain sliding window of text. And on the very bottom of the model, so this is the second input of the model, you have the question you want to ask. And so basically what you will do, you will start the X here, the XI here, all the pieces of text that represent the text you want to be able to answer a question from. So you will transform with the function phi, that can be an LSTM, that can be a CNN, that can be just a bag of words. You will transform those pieces of text into a block of memory. A is actually a transformation matrix, which is a parameter of the model. You will do the same thing for the question. You will transform it through a function phi. That, as I said, can be an LSTM, can be a 1D CNN. And you will transform this question into what we call the first state of the controller U. You will have also another transformation of the text you need to do, which is actually what we call the writing blocks. And what you do basically is that once you have computed the first controller and the first reading block here, you actually compute an attention over the blocks. So you look how each of the block M makes sense regarding the current state of the controller. And using that value P, you actually create a vector O, which is actually an output from the representation of the memory that is here. And then, using that vector O that you just compute, you update the value of your controller. So here it's a very simplistic update that was proposed at the beginning in 2016 when this model was introduced. And once this controller is computed, you can do it again. So that's why here, for example, in this specific model, you have 3 layers. In memory network, people call that hops. So it means that 3 times you will actually you will observe your data, update your controller. Observe your data, update your controller. And once you arrive at the very end of your reading capability, you will actually project over a set of possible answers. So here you see the capability of the model of perceiving several times the same input by sequentially integrating new information. An interesting aspect in this model, as you can see, is that it's fully differentiable. So it can be actually optimized using stochastic gradient descent and using a categorical cross-entropy or binary cross-entropy, depending on the type of output you have. And for the hyperparameters, like for example the amount of hops or all the parameters linked to the optimization algorithm, you can use grid search. A proposition we make in 2017 with my student Feliu, which is a PhD student from Melbourne University. It's a work we did during his internship at NLE. We actually propose to transform that deterministic update using actually a gated controller. That's why we named the model gated memory network. By doing so, we were actually able to choose which parts of the output will be actually used to update the controller. So here you see, you start by compute the gate, which is actually a sigmoid over a transformation of the current state of the controller plus a bias. And using that value, here it's the element-wise product, we actually choose what we keep from the previous controller and what we take from the newly computed OK. And then for the decision at the very top of the model, the decision remains the same. So we actually propose an end-to-end trainable regulation mechanism for accessing the memory. And that model is actually inspired by what Professor Jürgen Schmidhuber, the inventor of LSTM, called highway networks. In terms of results, we started by experimenting our models on those 20 tasks I was just presenting before, and we were quite happy at the time of publication to be state-of-the-art in those tasks. It was really important to show that some tasks were already really well handled with memory network, but by improving on the task that has the most trouble, like for example positional reasoning, for example, we did not actually degrade the performance on the other tasks. Now the second application I will talk to you is actually dialogue state tracking, and how that family of model has actually been proposed and used for this task. First of all, I need to present the task. Dialogue state tracking and a dialogue state tracker is a fundamental module of a modular dialogue system. The idea of a state tracker, dialogue state tracker, is to maintain a distribution over value for latent variable related to a transactional dialogue. Here, for example, a very, very classic type of dialogue people use in dialogue research is about booking a restaurant. When you book a restaurant, one of the information the system needs to know is the type of food you wanna eat. And so here, as the system is actually speaking with the user, you have that module, the dialogue state tracker, that actually update its belief over those latent variables that will be necessary to perform the task. Since, I would say, 2005, each year you had actually a challenge, a dataset challenge called the Dialogue State Tracking Challenge, where actually people were competing for these machine learning tasks on different type of datasets, mostly related on transaction of that kind. But we actually have a lot of limitation on the current model that was proposed, that was basically deep learning model like LSTM and Bayesian networks. The very first problem was the longer context. Often in dialogue, in order to be efficient, we use reference to what we said before, and sometimes longer before. So we need to have a model that is able to handle that kind of capability. Another thing is being able to have a looser supervision schema. What do I mean by that? Everybody that makes machine learning in this room know how annotation is a problem. And if you look at this data set, you have to annotate every sentence. So if I want to create a data set of that kind, I need to annotate every sentence with all the variables I need to be able to track. That's a problem. And the very last one is reasoning capability. I will give you a very simple example. I want to be in Seoul on Monday. 5 days before, I want to be in Paris. And 2 days after, I want to be in Prague. When should I be in Prague? So that's the kind of model we want to be able to learn. So what we propose this year, still with my student Feliu, was actually to define the problem of dialogue state tracking as a reading task. So what does it look like? First of all, the dialogue will become the text that you are supposed to be able to read. The question will be, in this case, related to the variable you want to be able to track. Like, for example, here the variable I'm trying to track is the price range that the person wants for the restaurant is looking for. And the answer will be actually the value. So here you see that what we said before is actually pretty, I would not say solved, but start to be answered. First of all, you see here that I can put a question wherever I want. I don't need to necessarily have an annotation at every sentence. I can have actually an annotation only at the end of the dialogue if I want. And then if I have a huge amount of dialogues, I will actually ask my question at any stage of my dialogue. Regarding reasoning capability, as I will show after, I will be able to actually maintain my attention to actually have, if possible, the capability of reasoning. And for the very last thing, because here at any time we're considering the overall dialogue, if I need an information at the very beginning of the dialogue, I will actually just have to drag my attention over it. So here the fact that because the attention is done over a memory that is non-parametric, I can actually handle it. What I mean by non-parametric is that for people that know what is an LSTM maintains its memory in a fixed length, which is the value of the h. So either you have an overall book to remember, or a sentence, you will use the same vector you will define in your LSTM. Here, if my text grow, the size of my memory grow, but I'm still differentiable. I can still use SGD to learn my model. And so that's what we have done. And actually, in terms of performance, we were pretty happy because we could actually show that we improved the state of the art on the dialogue state tracking to data sets, and even the tree, actually. Finally, end-to-end dialogue learning, which is actually one of the most difficult tasks we have today. Often when we discuss with famous people in machine learning, and especially in deep learning, end-to-end dialogue system is one of the tasks they perceive as the most challenging challenging today with visual question answering, among others. So what is end-to-end dialogue system? The idea is pretty simple to summarize. As we saw before, annotation is always a difficult task, very expensive, and can change through time. When you basically work with dialogue, most of the time, the data you have is dialogue. You can have hundreds of thousands of them, but you have dialogue. You don't have annotation. Maybe sometimes you have metadata associated to dialogues or associated to, for example, the user profile or that kind of thing. But most of the time, the main thing you have is dialogue. So it would be nice if we can actually try to learn a dialogue agent only from those dialogues. Maybe we can actually, as at some point Facebook M did, we can actually hire people to start answering the request of users, register what they say, and then start creating data sets from this. Another point that is quite important is that basically most of the time when you are a dialogue system, you interact with a knowledge base. It's not just about dialoguing, it's about doing something. And often that doing something means you need to be able to interact with a knowledge base or with any kind of services that is in the back end. So here, what I show you on the right-hand side is actually a data set that has been produced at that time by Facebook AI Research that was about dialogue for, the transaction is often a restaurant in our research, but you have other type of dialogue that also exist. But here what you observe, if you look at the dialogues, you have that kind of sentence that looks like a sentence. It's actually an API call. So it means that the system, yes, I'm using line. Okay. You see here basically that the system is actually choosing either answering to the user or performing an API call. Another thing that you see in this second example here are actually return from the knowledge base. So it means that I can put different type of object into my memory. When I want to choose what I need to say next, I can take as a support for my decision what has been said so far, and some return from the knowledge base that has been taken from a previously done API call. But I'm still having the same model that is fully differentiable. So we are actually, in that case, answering the different issue we had as we design a dialogue system, choosing how and when to interact with the backend, answering to the user, and as much as possible using the data that is the most available, which is the dialogues themselves. And to finish with this slide, the question you can ask is how you formalize this as a machine reading task. The answer is, let's assume the text so far and the pieces information that has been extracted so far from the knowledge base is actually the text. The question would be the very last utterance given by the user, what he just said to you, and the answer is actually what you're supposed to answer to this. Oops. Sorry. So what we did is we basically compare ourselves, our gated memory network, to the model that was proposed by Board and Weston in 2016, and we tested on the different tasks that was proposed on that data set. The idea was actually to decouple the overall dialogue from different type of problem that you have. First of all is issuing the API call. If somebody asks for something, you can actually define the first subtask of the dialogue as finding the proper API call that you need. Then, updating the API call means, okay, the user has asked you something, you have made an API call, it changes his mind. So you have to update the API call. Or maybe you observe that the constraints he gave to you have no results in the API call. Maybe you want some kind of restaurant in a certain part of the city that basically does not exist. So you need to actually update the API call. displaying the option is when actually you have more than one possible place, for example, one possible entry on the knowledge base that corresponds to the constraints that have been given by the user. Providing information is actually when, for example, the place has been found and chosen, and the user wants to have more information about that place. So it's another type of API call linked to a certain place that was chosen. And full dialog means that you will actually test your system at any moment on a full dialogues. So not for a specific of those subtasks. The second family of tasks are actually using out of vocabulary situations. So it means that in the test set, you may have places or words that has not been present in the dialogue. And finally, the task 6, which was the most difficult, is actually true dialogues. So those one was actually simplified dialogue that were properly defined for the task of transaction on restaurant. The T6 was actually the dialogue state tracking dataset was actually human against a simple machine, but with real human that was interacting with it. And what we used in this experiment is two types of protocol. On the left-hand side, the memory network and the getting memory network were used without any features of any kind, just the text and the API call. On the right-hand side, we use what we call the matching features. The matching feature is the fact that we added to the description of the possible answer some information related to the fact that some words was actually belonging to the text. So this was just saying that if I have to choose that answer as candidate answer as an answer, I will not have just the bag of words of that answer, but also the information informing the model that if some words are actually also present into the text. And we are actually showing that for most of the tasks actually, and especially the tough one related to out of vocabulary and more realistic setting of dialogue, we are actually performing pretty well. But as we see here, for example, in accuracy, we are still pretty low in those hard type of dialogue, which means that we still have a lot of work in order to be able to train a model and to produce a dialogue system using that kind of model. Before concluding, I want to show you, as I said before, that an interesting aspect is also having an interpretable model, or at least having more insight on why the model is actually working and what was actually the support for the decision of the model. And in our gated representation and using the attention, we can actually visualize the pattern of attention. So here, for example, is an example of a tree-up memory network. So here is 3 prototype attention activation that was clustered on an overall dataset. So to be more precise, we basically pass an overall dataset of question answer on the model that has been trained. We have recorded the attention patterns. So here, for example, it was a tree hop with actually around 30 sentences. And we see the type of pattern. So here, for example, the model activates on the first at some peaky level, then is flat at the second, and will become activated at the third. Here only at the first, and then stop reading, and here only at the third. So what is important to understand is that each of those hops has different parameters for the access of the memory. So what is also quite interesting here is that if you take, for example, that second pattern, what it means is that the model is reading the memory, then it stops reading. Here, the two first transformation does not fit with the value of the controller. That was the transformation of the question, but on the third one, it was actually choosing to extract information from the memory. So it's still a very simplistic way of observing the model, but those attention can be seen as first tools to try to interpret the model decisions. And I want also to emphasize the fact that this gate that we proposed was actually a first proposition, and we think there's still a lot of work to do in order to improve and to understand how this differentiable access of the memory can allow us to go toward a neural Turing machine. In order to conclude, I want to emphasize the fact that the goal of our research is basically to automate repetitive cognitive tasks, call centers, assistive tasks related to repetitive dialogue type of tasks. And one of the means we try to use is to actually having an end-to-end training over reasoning capabilities. And as you know maybe already, that's an extremely open and active field of research. Here, for example, I have shown you mainly examples related to text. We also currently work on models where actually images are encoded into the memory in order to perform visual question answering, for example, or visual dialogue. Visual dialogue is the kind of thing that is used, for example, for in order to describe images to blind people and allows them to actually not only just having a caption of the image, but being actually able to also ask questions over the image that they cannot see. But we need to understand that we still have a strong lack of theoretical analysis. We still don't know what are the proper conditions for our optimization algorithm to converge. We also have a lot of misunderstanding of what is actually the nature of the loss function. So it's very related to deep learning anyway, but in the case of those attention models, we often observe phase transition and different kind of behavior of the loss function that make the training sometimes pretty difficult. And then come the very fundamental question of learnability. So having formal condition on if a certain type of task can actually be learned by a memory network or that kind of model. And finally, we think that beyond the architecture of the model, the procedure of learning, the process of learning need to be revised and strongly questioned. In all the example I gave you today, it was basically supervised learning. We know in practice active learning is extremely interesting, not only because it's efficient, but also because it acts as a curriculum learning. The idea of the curriculum learning is basically to start by the simplest example. It's an example of a curriculum learning process, but basically being a bit more thoughtful in the way you actually choose which example and the way you update the model. Finally, regularization strategy. So far, the regularization strategy that we use in deep learning are basically for L2 regularization is based on what we used to use in logistic regression. We also have things like dropouts and early stopping that are more linked to neural network. But we observe that in the case of an attention model, sometimes, for example, what you want is to make sure that the model is able to make proper attention shifting. Something that you observe sometimes, I could have shown you some example, you have the model that actually fixes in the part of the text and cannot go away from it anymore. Because there was so much information here that it cannot actually shift from one place to another. I didn't have time to show you, but in gated memory network, we observed that because of the fact that the access of the memory becomes differentiable and is not deterministic anymore, we observe a diminution of that problem, but it's still a problem. So that's all for me. So if you have any question, thank you.